Welcome to The Explainer. Today, we're going to dive into some hidden chemistry that's all around us. It turns out that the secret to making great pickles, keeping your car engine from overheating, and even what goes into a hospital IV drip, well, it all comes down to the exact same, surprisingly simple scientific principle. Yeah, I know, it sounds like a totally random list, right? But they are all connected by one really powerful idea that's quietly at work in our everyday lives. And you've definitely seen this stuff happen before. Think about how a raw mango just shrivels up when you stick it in salty brine for a pickle. Or how we salt the roads in winter to melt the ice. Or, how a sad, wilted flower suddenly perks right back up in a vase of fresh water. The science behind all of this is exactly the same, and it is absolutely fascinating. So what's the secret key here? What unlocks all of these mysteries? Well, it all comes down to one core idea. It's not about what you dissolve in a liquid. It's all about how much you dissolve. This big idea is called colligative properties. And the name itself actually gives us a huge clue. It comes from the Latin for bound together. These are properties of a solution that are all linked together, not by what the dissolved stuff is, but simply by how many particles of it there are. The best way to think about it is like a crowd. A crowd causes a traffic jam because of the sheer number of people, right? It doesn't matter if those people are doctors or lawyers or artists, it's just the quantity. Well, chemistry works the same way here. It's the number of particles that matters, not what kind of particles they are. And this whole idea was really nailed down by the French chemist François-Marie Rault. He's the one who figured out that when you dissolve something that doesn't evaporate easily, like salt or sugar, into a liquid like water, the thing that really changes the liquid's properties is just the concentration, how crowded it is. This is the foundation for everything else we're going to talk about. So how does this crowd rule actually play out? Let's take a look at how just adding these particles messes with the liquid's ability to do things like freeze or boil. Okay, so adding that crowd of particles kicks off this chain reaction, and it leads to four main effects we can actually measure. They all grow out of that one single principle Rault discovered, and I bet two of them are way more familiar to you than you might think. So two of the big ones are freezing point depression and boiling point elevation. Basically, when you add a solute, those little particles get in the way of the water molecules. They make it harder for them to line up neatly into a crystal to freeze, and they also make it harder for them to escape into the air as a gas to boil. This is exactly why we throw salt on icy roads. It lowers the freezing point of water. And it's why the antifreeze in your car doesn't just prevent freezing, it also raises the boiling point to keep it from boiling over. But here's where it gets really powerful. Scientists can actually flip this whole thing around. By measuring these little changes in temperature with a lot of precision, they can work backward to figure out something super fundamental about a substance they don't even recognize. It's molar mass. It's basically chemical detective work. Let's just walk through an example. So you start by measuring a tiny, tiny change in the boiling point. In this case, less than 1 degree. You already know how much stuff you mix together, so you just plug all those numbers into the standard formula, and from that one little temperature reading, you can solve for the one thing you don't know, the molar mass of your mystery substance. And just like that, you get your answer. In this case, the calculation shows the molar mass is 58 grams per mole. It's amazing, really. Just by measuring a temperature change, we've figured out a key piece of this substance's identity. All right, on to the fourth property, which is hugely important in biology and medicine: osmotic pressure. This is all about the natural tendency of a solvent, usually water, to move across a barrier, like a cell wall. Water wants to go from a place that's less crowded with solutes to a place that's more crowded. It's trying to even things out. And this is happening inside our own bodies constantly. Our blood cells have a very specific concentration inside them. That's why an IV drip has to be isotonic. It has to have the same concentration, like a 0.9% saline solution. Because if the drip were hypertonic, that's too salty, water would get sucked out of your blood cells, and they'd shrivel up. And if it were hypotonic, not salty enough, water would rush into the cells, and they'd swell up and pop. So the main takeaway seems to be, it all comes down to just counting the particles. Simple enough, right? Well, what happens when the particles themselves
don't exactly play by the rules.
This is where it gets really, really cool. I mean, what if you dissolve one particle, but the second it hits the water, it splits into two? Or what if two particles decide to team up and act like they're just one big particle? Suddenly, the number of particles you actually have in the solution is different from what you thought you put in. To deal with this, a scientist named Jacobus van Hoff came up with a brilliant fix back in the 1880s. It's called the Van't Hoff factor, and we use the letter I for it. You can think of it as a correction factor or reality check. It's a number that tells you how the solution is actually behaving compared to how you'd expect it to behave.
So if you dissolve something like table salt, NaCl, it dissociates. It splits into two separate ions, a sodium ion and a chloride ion. So you've effectively doubled your particles. That means its I factor is going to be greater than 1. But then you have other things, like acetic acid in certain solvents, that do the opposite. They associate, or team up into pairs, which actually reduces the total number of particles. So their I factor is less than 1.
And you can see this perfectly in the experimental data. Just look at NaCl. In a perfect world, it would split into two particles, giving it an I value of exactly 2. Now, at higher concentrations, the ions are a bit crowded and stick together, so the value is a little lower, like 1.87. But as you make the solution more and more dilute, the ions have more room to roam, and that I value gets closer and closer to that perfect 2. Okay, so now that we have the full picture, we know we have to count the particles, and we even know how to account for them splitting up or teaming up. So how can we use all this knowledge to tackle some really big real-world problems? Let's go back to osmosis for a second. We know that water naturally wants to flow towards the saltier side of a membrane. But what if we physically pushed on that salty side? What if we applied a pressure that's even stronger than that natural osmotic pressure? We can actually reverse the flow. We can literally squeeze pure water away from the salt right through that membrane. This is the principle behind reverse osmosis. And honestly, it's a total game changer. This is the technology that desalination plants all over the world use to get fresh, drinkable water straight from the ocean. By using a special membrane, they can filter out all the salt and other gunk, leaving pure water behind. And that all comes back to that simple, fundamental idea of just counting particles in a solution. It really makes you wonder, doesn't it? If understanding a basic principle of chemistry can lead to technology that gives millions of people drinking water, what other massive challenges could we solve just by exploring the science that's hiding in plain sight all around us?